Hey guys, today we're going to be looking at types of chemical reactions. As we saw yesterday, chemical reactions are where you take some chemicals that can be elements or compounds. You react them together to make something new. So you start off with some reactants, and those are going to form a new product or some new products depending on the situation. There's 5 types of these reactions that we're going to be looking at today. The first one is called synthesis. So synthesis takes some elements or compounds, really any two things, and forms one new compound. So you got 2 things and you're going to add them together. Our example here is we've got some potassium and some chlorine all by themselves, and they're going to get together to form potassium chloride. And as always with any type of equation, you do have to balance it out. That's achieved with these coefficients. You can work that out on your own if you would like. But the key thing to see here is that you've got these 2 reactants that combine together. Now note that the Cl has a 2 here and it doesn't over here, and that's because of ionic charges. You know that potassium is a +1, chlorine is a -1, so when they form a compound that makes KCl. So that's why you have to do the balancing, is to make sure that you have the appropriate numbers for each thing. And we're going to be talking about these with the metaphor of dating. So what you can say with synthesis is you've got 2 single elements all alone by themselves, poor lonely guys, and they're going to get together forming a new relationship, which is a compound, because now they're bonded together. So they were single, now they're together. That is called synthesis. Awesome. Next up is decomposition. Now, decomposition may sound familiar from biology class. And in biology class, you learned that decomposition is the breaking down of organic substances. And chemically, it's the same idea. Decomposition is when a compound breaks up into its elements or into more simple compounds. So you'll start with some reactant, just one reactant. That's how you can tell it's decomposition. And it's going to decompose into its 2 individual elements. Note that here Cl has to be Cl2 because that's a diatomic molecule. And as always, you would balance these things out the same way. Basically, it's this reaction from above going backwards. Sorry, I just realized I had weird music going in the background, so that's going to end now. Anyways, decomposition, as we said, is breaking apart a compound into simpler compounds or into its constituent elements. And in the dating metaphors that we're using, this would definitely just be breaking up. You have a compound, a relationship that's perfectly fine together, and then they split apart into the individual elements, they break up. Our next type of reaction is called single replacement. This is where it starts getting a little bit juicy. In single replacement, you're going to have a lone element all by itself, and it's going to replace another one in the compound. So let's look at this example here. You've got zinc all by itself. What a lonely, lonely element. And you've got hydrochloric acid over here, all happy and contented in a relationship, or so we think. But what you can see over here on this other side is that zinc is going to steal chlorine away from hydrogen and kick hydrogen out. So on this side, zinc is with chlorine and hydrogen is now alone. It's like zinc totally stole hydrogen's girl, ran off with chlorine. Now they're living happily ever after, and hydrogen's single and lonely. What a depressing story for hydrogen. So a closer look at what's happening here is necessary for when we get on to predicting products later, cutesy metaphors aside. If you look at the zinc here, you know that zinc is a transition metal, which makes it a positive ion when it forms a compound. Zinc is positive. Now, zinc is going to steal from this compound, and it's going to steal the negative, because zinc is a positive, it wants to get with a negative. Chlorine here is a negative, hydrogen is the positive. So zinc is going to boot hydrogen out, the positive thing, and take over chlorine, the negative thing. trying to have zinc with hydrogen and kicking chlorine out would not work because you've got to have the positive going with the negative, which you can see over here. Positive zinc goes with negative chlorine, hydrogen is left out. Now this can occur with a negative element that is single, and we'll look at an example of that down here. So here you've got sodium chloride, happy relationship, and fluorine single by itself, and it is a negative ion. So the negative fluorine needs a positive to go with it. Out of sodium and chlorine, sodium's the positive, so fluorine is going to get with the sodium, the positive, to make sodium fluoride over there. And that leaves chlorine out on its own. So you're going to have a positive and a negative together, and the negative left out. Now, another thing that we're going to look at more with predicting products is when this can happen. So sometimes you'll have a single element and a compound, and nothing will happen. There will be no reaction. And that's because of a thing called the activity series for metals, or the electromagnetic trend in the periodic table for nonmetals. And essentially, going back to the metaphor, what this means is that the single element has to be hotter than its counterpart that's in the compound. Otherwise, it's not going to be able to split up the couple. So if we're looking back here at this first example, you've got zinc is stealing chlorine from hydrogen. Zinc has to be more attractive to chlorine than hydrogen is in order for zinc to steal chlorine. And there is a list called the activity series. It's on the back of your periodic table, or the back of the star periodic table charts. It's on the same set of things as your polyatomic ions list, but it's called the activity series. And the hottest elements, or most attractive ones, are at the top, and the least attractive are towards the bottom. So if you go look at that, you see that zinc is higher up than hydrogen, so zinc is more attractive. So chlorine will leave the hydrogen to get with the zinc. But if you started off with hydrogen alone and tried to get hydrogen to break up zinc and chlorine, hydrogen wouldn't be able to do it because it's not more attractive than zinc. And again, that list is in the activity series. Now, with nonmetals, it's not quite so simple. You don't have a straightforward list. Instead, you have to use your periodic trends, where you know that things get more electronegative as you go to the right and more electronegative as you go up. So you'll have to use the periodic trends. And you'll see that fluorine over here at the top of the column is more electronegative than chlorine, which is below it, so it can boot the chlorine out and take the sodium from it. Now that's very, very complicated, and we're going to look at it more with predicting products. For now, what you need to be able to do is identify something as single replacement, saying that zinc is a single element, it's booting hydrogen out, joining the compound, and hydrogen's left out on its own, so that's a single replacement. That's the skill you need to know today. Everything else there is a precursor to predicting products, which we'll look at tomorrow. All right, moving on down here to double replacement. Double replacement gets even crazier than single replacement. It is when you have two happy couples, like right here we got potassium sulfate and barium nitrate. Yes, you still have to know how to name things. And their cations, their first elements, the first partner in the relationship, they're going to swap, and they're going to switch partners. So potassium is going to end up with nitrate, which is right here, and sulfate is going to get with barium to make barium sulfate over there, which is pretty crazy in relationship terms. That's two couples, swapping partners. And you can tell something is double replacement if you've got two compounds initially, and you've got those first two elements or first two ions are going to swap. Now, something you do have to watch out for in these is called the precipitate or precipitate. Looks like precipitate. And there's going to be a chart, the solubility chart, that we use to predict precipitates. We're going to look at that more later in predicting products again. But those precipitates are solids that are formed whenever a double replacement reaction happens. Most double replacement reactions occur in solutions, so while they're dissolved in water. And they'll be all dissolved in the beginning, and then when the reaction occurs, one of the products will be insoluble and will form a precipitate, which is like a solid in the solution. And we symbolize that with this little S and the down arrow. But again, more on that later when we get to predicting products. For now, you just need to know what a double replacement reaction looks like, what's happening inside of it, and how to pick one out of a lineup. All right, last type up is combustion. Combustion is basically when things explode. It's pretty cool. Probably the coolest of all the reactions, but unfortunately does not have a dating metaphor. If you think of a good one, please let me know so I can incorporate it into next year's curriculum. But what combustion looks like is it's a hydrocarbon. Hydrocarbon is a combination of hydrogen and carbon. Cool. Usually things sound like methane or propane or butane. Those are all hydrocarbons. So it's going to take that hydrocarbon, react it with oxygen, O2, and it's going to form CO2 and H2O. So anytime you have a reaction that looks like something reacting with O2, making water and carbon dioxide, that is combustion. Really, it's just something you gotta learn, gotta memorize. Reacts with oxygen, makes carbon dioxide and water is combustion, which is the coolest of all reactions. Not true. There are cooler reactions, but it's the coolest of these reactions. And as always, even though I haven't done it on the last couple of examples, you should balance your equations in the end. Usually combustion reactions are some of the harder ones to balance. Again, if your teacher didn't tell you, you probably want to balance oxygen last in these things. So let's balance this one for funsies. You would start with an element that's not oxygen. I'll start with carbon. Carbon's got 5 on this side, 1 on this side. Add some more. You can't add just carbon by itself. You have to add the whole compound that's already there. So we add a bunch of CO2s till we get 5 C's on each side. Then you look at hydrogens. 12 hydrogens there, 2 hydrogens there. Got to add some more. Now we've got 4, 6, 8, 10, 12. Awesome. And last is oxygens. You've got 2, 4, 6, 8, 10, 11, 12, 13, 14, 15, 16 oxygens on the right, which means we got to get up to 16 over here on the left. Now we got 4, 6, 8, 10, 12, 14, 16 oxygens. And everything's balanced. You count it all up. You've got 1 C5H12, 1, 2, 3, 4, 5, 6, 7, 8 O2s, 5 CO2s, and 1, 2, 3, 4, 5, 6 H2Os. A nice, lovely, balanced combustion reaction. Again, combustion reactions are usually the hardest to balance because they don't necessarily work out super nicely. All right, there should be some practice in Google Classroom over types of reactions where you'll have to balance reactions or balance equations and write the type of reaction on there. These are super important. They are a necessary prerequisite for doing predicting products, which will be next class. And you're going to have them down pat for the rest of the semester. So make sure you understand these. If you don't understand them, if you're having trouble with practice, as always, feel free to contact your teacher, come to office hours, or just rewind this video, watch it again until you get it. Hope y'all are having a great day and that this makes sense.